is very, very important because uh, because mm, if you are used to, if you get used to this Dirac notation, then life becomes very easy. So let me start by presenting. So I can make it bigger. I think this is fine. Yeah. Okay. So let me start by saying there is something called state space. This is called state space shown here. And so it tells you that this is a different approach, not the usual wave function based approach to quantum mechanics, but is equivalent. It says that each quantum state of a particle is characterized by a state vector, okay, belonging to an abstract space. So it is just another space like a Hilbert space, a subspace of Hilbert space. And this abstract space is called state space. And we use notation for this state space. These notations are called Dirac notation. So any element or vector in this space is called a Kate vector. And it is also called a Kate, simply a Kate. And this is how it is represented. Okay, can you see the sign, all of you? This is the way it is represented. Can you see? Please write down in the chat box. Can see? I hope you can. Yes. Okay, so okay. So this is how the is represented. Okay. Uh, okay. Now, earlier we had this approach. This is called wave function based approach, which you have been doing so far. Where your wave function is here. So this is a function of space and time. Okay, I'm not considering time for the time being. So this is psi of r, or we are doing many times. We are doing like this, psi of x. There's x dependence or r dependence. But when you go from your wave function based approach to Dirac notation, then you have a Kate vector shown here, and here this r or x or any space dependence is no longer shown. So space dependence no longer appears. This is very important. So no longer space dependence appears, and that makes my life actually easy. We'll see how. So we have now introduced there is a space. In that space, you have elements. They are called Kate, and they are represented like this, shown here. Okay. And then there is another space, which is the dual space of the space where the Kates belong. And in this dual space, which I'm shown here, this is a dual space. This dual space shown here. In this dual space, we have elements or the vectors. They are called bra vectors or bra, and they are represented by this symbol. Okay. And the most important thing that to every Kate there is a bra, corresponding bra. To every Kate corresponds a bra. This is very important. Very, very important. So you understand? So you have this space and we have this space. This is the dual space. Here all the elements are Kate. So they are represented like this. Here all the elements are bra. They are represented like this. And between, for every Kate there is one bra. So there is a correspondence. To every Kate corresponds a bra. So is it fine? So let me write down something which we have introduced in the last class. This is called inner product. How many of you remember inner product? There's another name to that. What is that? Can you write down in the chat box? What is that called in our product? Yes, scalar product. It's called scalar product. But we had used, we had shown these inner products or scalar products in the wave function formalism. But what happens here? Remember that earlier we had done this. Now, if you had wave function, and in the last I showed you the inner product is shown like this, which is equivalent of saying, okay, you integrate. I assume this is in dx, in x, you can put d tau if you want. Or this is something like 5 star ix. Remember, all of you? Just recall.
Yes, sir.
Okay. But now let me do this inner product. Let me define this inner product using bra and Kate notation. So if I use bra and Kate notation, this is going to be nothing but now the point is, if I write a Kate before the comma inside this first bracket, what does it mean? If it is before the comma inside the first bracket, can anyone tell me? Can anyone guess? Because if you go back, if you see that if I write a wave function before the comma, that wave function becomes what? You have to take complex conjugate of that wave function. So here also, if I write any Kate before the comma inside the first bracket, that Kate would become a bra. Okay. So this is equivalent of saying that it is an inner product between a bra phi and a Kate psi, and this is given by this symbol. This is very important because many times we are going to use this symbol. This is called Dirac notation. Is this clear? This is very easy in a sense because I don't need to write the integral sign. I don't need to write dx, deta, whatever, then put the integral, the limits of the integral, but I can write this way. Is this fine? Because there is a one-to-one correspondence between the wave functions in this one Hilbert space, and then that another this subspace of Hilbert space where these Kates belong. So there is a one-to-one correspondence between each phi and a phi Kate. Similarly, between phi star and bra of phi. Okay, is this clear? So let me see. Let me check some properties, which is obvious. If I take this, multiply a Kate with a number, what should be the answer? How would I write this? Now, this is nothing but I can put this inside, and this. This is not difficult to understand, isn't it? But if I have something like this for a bra, what should be there on the right hand side? Can anyone tell me? Can
lambda star.
Lambda
Yes.
Lambda star.
Complex conjugate of lambda.
Yeah, because it is associated with a bra. So don't forget when you take it out, because lambda in general is what is known as a complex number. Remember, whenever in quantum mechanics, if I multiply with a number or any coefficient, that coefficient would be a complex number, isn't it? Okay. So this is, you should take that that lambda star outside and then put the psi, isn't it? This should be like this. Rahul, you are there, no, today? I think Rahul is there. So now let us try to find some inner products. Let me try to find some inner products.
Yes, I am there.
Yeah. So let us take a linear combination of two Kates like this, and take an inner product of the whole thing with another Kate. But since this is before the comma, this whole thing is going to be what? You know that? The whole thing is going to be, so this is equivalent of
Conjugate.
saying, yeah, it should go to the dual space. So lambdas should become lambda stars, isn't it? So what I should have, I actually lambda 1 star, then this and this, psi 1 psi, plus next thing would be lambda 2 star, psi 2 psi. Are you fine with this? Are you fine? Let me know if you are not fine, then this is not very difficult. Please write in the chat box that, okay, sir, I am fine. Yeah, fine. So, yeah, this is very straightforward. Now, what is this? I can write this in a slightly different fashion because I can put a this like first bracket here, and first bracket means this is different sense, and I can say that, okay, see, there is no comma here, so I'm just writing this again. Just I'm putting a first bracket. Okay, you understand what I'm doing? I'm just putting a first bracket, no comma here. So this is used in sense of bracket. So what I have here is this. Now what it essentially tells you? It essentially tells you that if I take a scalar product between this bra and psi are all this one and psi essentially the same, it tells you that there is a correspondence between this quantity lambda 1 psi 1 plus lambda 2 psi 2, actually lambda 1 star psi 1 plus. So it tells you that Kate, I told you that for every Kate there is a bra. So it also tells you that Kate to bra correspondence, there is a correspondence, is antilinear. See, this is antilinear. I did not mention before antilinear thing. Antilinear means when I change, when I multiply this lambda 1 with psi 1, if I want to do the same thing in the bra space, in the Kate bra space, then I should multiply that bra with lambda 1 star. You understand? This is exactly what I said. What I meant here. Is this clear? This is called Kate to bra correspondence is antilinear. It would have been linear if we had only lambda 1 or lambda 2, not star. Since we have a star, because Kate and bra, they belong to Kate belongs to a state space, and bra belongs to another state space, which is a dual space of the Kate space, isn't it? That I showed you here. Whatever this epsilon shown here, the curly epsilon. This is a state space where all the Kates belong, and this epsilon star is another state space where all the bras belong. But this epsilon star is actually a dual space of epsilon. So because of that, the correspondence between Kate and bra is antilinear. Essentially, by antilinearity means this: when you multiply your Kate with a number, then there is a corresponding bra, and that bra should you should do, if you try to do the same operation in that space, then you should multiply that bra with a complex number, same number but the complex conjugate of that. Sorry. Okay, so this is how it is. So far we are fine. I'm sure not very difficult what I'm doing so far. I can ensure you that when you get used to with bra and Kate notation, your life becomes easy. Okay. So now let me write another thing. For example, what happens if we write phi, which is a Kate. This is Kate or bra? This is bra, okay. And psi in the opposite order. You're getting my question? So the by opposite order means, say for example, phi or psi or psi or phi, whatever. Let me do this way. Yes, psi to phi. Is it the same as phi into psi? Do you think they're equal or not? What do you think? Maybe someone can tell me. Rather than writing, someone can tell me. The actual answer is no, they are not same. This is called inner product. Or scalar product. What about the one on your left? This has a different name. This is called outer product. And this is different from scalar product. Wow. So let us define something like this, because if I take any arbitrary, any arbitrary Kate, say chi, okay, and say consider the following operation. What is the operation? So consider I take this and I take this guy and operate this on chi. You understand? So this is something like an operator. It's an operator. Why? Because when you put in front of chi, this will give me what? Because if you see carefully, this phi and chi, they are inner product. They are forming an inner product, isn't it? So what will? So if I take inner product between a Kate and bra, what should I get? Answer. What should I get if I take an inner product between a Kate and a bra? Can you write it down?
Or normalized the function, it will be 1. If it will be not normalized, it will be constant.
Yeah, so because they are different, so this cannot be 1. So essentially, it is a complex number. It's a complex number. It could be a real number, but make it more general. It's complex number. So essentially, what I have here is something like a proportionality constant, isn't it? Why? Because this is a complex number and I call it C. If I call it C, then what I have here is psi times C. Now you can put the C here or C outside. When you put, you can put anywhere. Let me put it here. So essentially, it tells you that when this operator operates on some arbitrary K, it gives you a fraction of something, psi. So essentially, this outer product is kind of an operator. So let me define something else, which is also an operator, but this is very useful. So let us define this operator. I'm calling it P of psi, and this operator is defined as psi. Outer product, of course, but of the same Kate or bra. Okay, is this fine? And now this is an operator, okay. Now if I take this operator and operate this operator on a Kate like phi, any phi, what should be the answer? This will be psi, phi. Are you convinced? Are you convinced? So again, this is a complex number. This is like proportionality constant. This is a constant. So I am just viewing it as proportionality constant. So basically it gives you something like which is proportional to psi, isn't it? Because this is something like some constant times psi. This constant could be a complex number, but like this. So that now what you are doing, you are operating this operator P of psi on a ket phi, and you are getting a constant times psi back. What does it mean? So essentially it is projecting phi onto psi. Is it clear? It is essentially tells you that how much psi is there in phi, in other words. So basically this operator, this P of psi, this is P of psi with hat, is gives you this orthogonal projection. Okay, operator onto the ket psi. This will be even clearer when I progress. Now if I operate this operator twice, what will happen? If I take this, I take a square of that. What is this? You know these are linear operators, so this is nothing but this. Fine. And now if I operate p psi square on say this phi, what will be the answer? Can anyone tell me? So let us see. So it is going to be p psi times p psi operating on phi, and I know you know that p psi is, you know, the definition, you know that this is actually phi, but then you have this p psi also, which you remember the psi phi. What is the answer? This will give you something, isn't it? But if I do the same thing, if I take phi psi square and operate this not on phi but on psi, what I'm going to get? If I operate this on psi, what I'm going to get? Can anyone tell me? If I operate this one onto psi, this is essentially again p psi times p psi on psi, and you know that this is p psi is your psi times psi. This is first p psi. Then I have to put another p psi, which is this into this. So this is another p psi, and then you have psi. What is the answer? Now psi, and these are normalized. This is 1. So if it is normalized, then what should be the answer? This quantity. Can anyone tell me what is the answer? Final answer? Yes. So this one is 1. So essentially what I have here is psi into psi, which is p psi, on psi. And this tells you that if I operate p psi twice, what I have here is equivalent of operating p psi once. This is another property. Is this clear? This is not very difficult. You must have done this. So the outer product, let me repeat, outer product, this is the way it is written. So this is outer product is an operator. So it does not give you a number. It does not give you a complex number or any real number. Inner product gives. And I showed you that this is how it is. It's the number, because if it operates on a wave function, not wave function, a gate, this is what happens. If I operate twice on this gate, it is equivalent of operating it once. This is just an operation. So it will be clearer when I introduce the next operator involving this outer product. So let us define, let us assume that you have an orthonormal set. Now orthonormal set means, I call it phi. What do I want to call it? You can want to call it phi. Phi is fine. Phi I, phi j. You understand? I am using Dirac notation. What should be there on your right hand side? What should be there on the right hand side? What is the answer? Please write it down. Some of you, maybe one or two of you. Zero? No, not zero. Sorry. This is called Kronecker delta. So never write zero. You don't know. In general, this is Kronecker delta. Okay. And I can define quantity like PQ. I'm calling it. So EQ is a number of basis functions. These are like basis functions, and I call it. I am defining an operator like this. It's an operator. So let us see what happens if I take PQ square. Now again, PQ square is PQ times PQ, which basically means the first PQ, let me write down. I want to, oh, sorry. Yeah. So whatever Q phi I into phi I like this. This is fine. And then I multiply this, because whole thing with another PQ, but I use a different notation for this. Not notation, different indexing. I call it J. Because that I should be doing this. Because if I use I in both the cases, I think I'll get confused. Okay, this is how it is. So then I can say, okay, this is equivalent of saying that, okay, I want to Q, J want to Q, okay. And then what you have here is the sum, you can take it outside, and then you have phi I. See what I have done here, phi I into phi j into phi j. I hope you are following. It is not very difficult. Actually, it's very easy. What is this quantity? Can anyone tell me? What is this? See, it is here, defined. Yeah, somebody tells me, yeah, no, yeah, delta I. So essentially what I have here is okay. Can I simplify it further? Yes, I can, because I know because of the Kronecker delta, only terms with I equal to j survive, only the diagonal terms, isn't it? Are you convinced that I equal to j will survive? Because that is how it is, isn't it? Because delta ij is 0 if I is not equal to j, is 1 if I equal to j. Remember, this is the definition of Kronecker delta. I hope you remember. Somebody tells me here. I am not looking at the chat box.
Yes, sir.
Yeah, yeah.
Yes, sir.
So what will be the answer? Dibojit, are you there? Tell me. Answer is actually I can get away with one of the sums. I will have this and I will have phi I times. And what is this? What is this? This is the one which is defined here. Isn't it? So basically what does it tell you? This is such an operator that the square of the operator is equal to that operator, isn't it? Okay. Are you fine with this?
Yes, sir.
And now let us take any kate, this psi, and this kate I represent as a linear combination of this basis function. These are basis functions, but they are kates. So as I did with wave function approach, here also I can write some coefficient Ci times phi I, and I go 1 to whatever the number of basis function. Actually, it is infinite, but I'm making it finite anyway. This is fine. This is nothing but psi equals to sum over Ci phi I. Huh? This is equivalent of, if you go back to your wave function approach, remember this? Whatever, I to n. We have done it many times. Somebody tells me.
Yes.
This is fine, na? I'm just using a cake notation, bracket notation, not the usual wave function notation. This is fine? Is this fine? I hope
Yes,
it is
sir.
fine. It's not very
Yes.
difficult, like I'm telling you. I'm just giving you I can ensure you that this is not difficult. Practice few times, you can get used. Okay. Now this is how it is. Now if I do this operation, if I take PQ and operate on psi, what should I get? What should I get? If I take PQ and operate on psi, what should I get? So actually, I'll get something like I'll get something like sorry. I'll get something like this is PQ. This is from here. So essentially, I'll have to psi. But what is psi? What is psi? Psi k. This is how it is. Huh? I can put it here. If I put it here, what I'm going to get? What I'm going to get? I'm going to get I equals to 1 to Q into phi I, and there's a coefficient I can put it here, Ci. Okay, Ci or whatever, Cj, you want to put it Cj is fine. I can put it phi j, and I can put this is a double sum actually. This is fine. I hope I have not done anything wrong. What I have done, I have replaced psi k with sum over Ci phi I. Please tell me, just switching on the microphone, someone of you, if you are following.
Yes, sir.
Rahul, are you there?
Yes, yes,
Yeah, I'm sure you are following. So I'm just asking the students. Any typo? Do you find anything? Yeah, any typo? Anyway, so what is this? What is this?
Kronecker delta.
Kronecker delta. Kronecker delta. Kronecker delta. So let us see. So basically, if it is Kronecker delta, then Rahul, I think I'm not doing anything wrong here. No, I hope I'm just going fine. Yeah,
yes,
this is
yes, yeah.
this is
But yeah,
Kronecker delta.
I just have
Yeah, tell me.
I just have one point to make.
Yeah.
I think during the course of your lecture, if you introduce just the fact that why this is a vector and why this projection
That I have done.
is a
That I have done in the
matrix.
last class. The last class. The whole
Okay,
class was
I was not
on
here.
vector
Okay,
calculus.
all right.
Yeah. The whole class was on linear vector space last year.
Yeah.
Last class was like that actually. Yeah. So this will give you something like whatever. It will only whatever Ci will survive and Phi. I'm just showing that if you play around with these operators, what you can get, isn't it? But again, I can do one more thing. What I can do, I can view this slightly different manner. If I view slightly different manner, if I view this, say I take this part. So look at it very carefully. I take one sum which is over I and take this guy. What is this? Then essentially I have Cj phi j sum over times this. See, I and j, they are this dummy variable. Okay, this is another way of viewing. So what I'm going to do, I'm going to put an arrow here. I'm going to put an arrow here. Okay. So if you now view that part, whatever that part is. So if I don't know, want to let me write down this way. If I view like this, I'll have j1 to q cj into phi j, and then I also have this whatever. Here I have multiplied this with which I have taken out. Are you following? Very simple, nothing else. Look at this sum. If you have a piece of paper, write it down there. Okay. So what I'm saying that, okay, this is phi j. Again, I'm telling you, look at it, what I have here. Cj phi I k, then phi I bra, then phi j k. This is one way I can use this Kronecker delta, it will give you Ci phi I. If I don't use Kronecker delta, I say the sum over I and take this phi I, this one, the whole thing. Okay, sum over I, phi and phi I. Okay. Okay. And then I am left with Cj phi j. Is it okay? Please tell me. Somebody can
Yes, sir.
unmute.
It is okay.
Unmute. Yeah. What I am saying that I am viewing it slightly differently. The whole sum. This whole sum is what? Sum over I 1 to q sum over j 1 to q, and I have Cj phi I phi j. This is your thing, isn't it? This is your thing. Again, I'm writing. Now, if I say, okay, now I want to take this part. Then what I'm left with? I left with sum over Cj phi j. Can you see that? Sum over Cj phi j, ket phi j. Please tell me yes.
Yes, sir.
Yes, sir.
Yeah. So this one I'm writing it here. So essentially I have sum over Cj phi j and then I have multiplied this with something. But j and I, they are just dummy variable, no? So this has to be equal to what? This has to be equal to the whole quantity at, okay, this Cj phi j is, this quantity is what? This is gives you psi. Now, if I, now let me call. Now I had said that I had put a value from I1 to Q. I1 to Q, okay. Now if I have a situation where Q goes to infinity, I have infinite basis set. So the whole space is filled up with this basis set, okay. So as a result, what I'm going to get that since this quantity, the whole quantity is psi times whatever your PQ, but then I can interpret this when in the limit, for example, when Q is very, very large, it goes to actually infinity. This operator is equivalent of saying this is an identity operator. Why? This is called identity operator. And so the way to write this is as follows. I can say, I just put only I there, phi I, 6. And this is called if Rahul wants to say something, he can say. Rahul, are you there? Rahul, are you there?
Yeah. No, yes, I'm here, but you go ahead. It's fine with me.
Yeah, so I am saying that maybe this is one way of introducing identity operator.
Yes,
What
that's
do
the
you say?
resolution of identity.
Yes. Resolution of identity. And this is true only when you're like you have infinite basis, isn't it?
Yes,
Essentially,
your space is complete.
it's complete. Actually, I did not use that word. Yes, space is complete. And so, because then this operator is such that if you operate this on psi, gives you psi back. And that is possible only when your space is complete, which will maybe I think Rahul will discuss it later. Okay. So this quantity, this PQ, if I write down in words, let me write down in words. This PQ defined here, it tells you that not PQ, yes, PQ acting on psi gives the linear superposition of the projections of psi. Onto various phi I, because there are many phi i's, no, onto the various phi I. So this is actually projecting psi onto the subspace EQ that belong to all this phi i's. Because there are q number of phi i's, so the EQ is the epsilon q is the subspace. They are projecting psi onto EQ. Now what Rahul says that if you're if you have a complete basis set, then this EQ q goes to infinity, infinite essentially. And then when you project psi onto this, you project the whole of psi, the whole of psi. If you project something, the whole of psi, then that is why the identity operator comes, because you are projecting the whole of psi. Otherwise, it is less than 1. You are projecting a fraction of it. If you are projecting psi, the whole of psi onto that space, then this is called identity operator. Okay, this is very important because when you proceed, we may use this resolution of identity. But now, what I'm going to discuss now, this is very important, and why it is important, because if you want to learn quantum mechanics, this is must. Okay. So what I'm going to define now, I'm going to define adjoint of an operator. So how many of you know adjoint of an operator? Adjoint. How many of you heard of? Tell me. Switch on the microscope. Hey, no, not the microscope, right? Microphone. How many of you? The of a linear operator A is written as how many of you know? I've heard about it. Tell me. Please unmute yourself and tell me.
We don't know, sir.
No, anybody knows?
So
Anybody knows?
something we know about the adjoint of matrix, not about operator. Adjoint of matrix or something down.
Yeah, adjoint
Similar
yeah,
like taking transpose and then complex conjugate.
Yes, that is what you do with matrix. It is similar. It is very similar. Okay. So let me define this. The idea is not very difficult. So if I take an operator A, operate on a kate psi, what I am going to get? Can I tell you? I'll get a new kate. A new kate, which we have done in the last class with wave functions. So I'm going to go A operating on psi. This gives you a new kate, which I'm calling psi prime. But remember, prime does not represent a derivative. So prime does not represent a derivative here. Now, you know that for every kate there is a bra. Okay. So let me schematically show you the scheme, and this scheme is very important. So what I have is this, where I take a kate, call it psi, and if I operate a linear operator A on this, what I'm going to get? I'm going to get a new kate, calling it psi prime, which is this. Are you fine with this? If I write that like this, this is fine. But for this psi, I have a bra in the dual space. I have a bra in the dual space, so there is correspondence between this kate and bra. Is this fine? Please unmute yourself, one of you, and tell me.
Yes, sir.
This is fine. This is nothing. So now what I do now what I'm saying that like in case of Kate, when I operate when I operate a linear operator A on Kate, it's like this, A operating on psi. But when I take a bra and operate the same linear operator, I cannot operate that. I have to take the adjoint of that operator and operate on that bra. So what is the idea? Idea is follows: not A, but like A dagger. Okay, A dagger that operates on this bra, and that gives you, of course, another bra which is a new, and this is equal to. Is this clear? Now this is not right because I have done a small mistake here. Ordering. You should write it like this. Your psi. It operates from your left. But just look at it. The psi prime Kate and psi prime bra, they should correspond to each other. No, there is a correspondence between this psi prime Kate and psi prime bra, because psi and psi, they have the one-to-one correspondence. Similarly, psi prime would also have one-to-one correspondence, and at the same time, the correspondence between the operators are like one operator and its adjoint. They have this correspondence, one-to-one correspondence. Okay. And this scheme is very, very important. I don't know whether you realize it or not. If you remember this scheme, you remember many, many things. And you can constant, you forget the constant. It's important. Okay. So how many of you could follow this scheme? So the idea is as follows. So if I have a Kate like this, let me write down here, not the crate, the bra like this, and then I operate a dagger on this, I get a new bra. This is how it is. For Kate, it is the other way. It is operating from the left hand side. It is operating from the right hand side of bra, and from the left hand side of this Kate. Okay, these are the rules. You have to remember the rules. Okay, you have to remember the rules. So you remember, I go back to the last class. If I write phi comma phi, this is equivalent of saying psi comma phi whole star. How many of you remember this from the last class? Please unmute yourself.
Yes.
Yes.
So can I write the same thing in what is that called? Using this is actually also I can This is also I can also do this with anything like phi. So can I rewrite this using bracket notation? If I rewrite this using bracket notation, you understand the left hand side is going to be this. You are convinced? Are you convinced that this is this? Are you convinced? Please unmute yourself and tell me, because
Yes,
I'm not looking at the chat box. Okay. This is fine. And what would be this one in terms of bra and Kate notation? This is nothing but, you know, this phi psi whole star. Okay, it is not very difficult. Anything on the left of the comma is a bra, anything right to that comma is a Kate. Fine. Please unmute yourself and tell me, some of you.
yes, sir.
Yes, sir.
I can hear only one or two girls. Where are the boys? Left already? Tell me. So no boys around.
Yes, sir.
So this is not very difficult. Huh? It's not very difficult. I'm just writing. I did it once, no? Okay. But like in the last class, what I did, remember, this is a new bra. This is a new kit. There also it is true for any psi phi. It is also true for psi prime. So similarly, I can write that, okay, if I write this quantity psi prime comma phi, first bracket, what should be there on the right hand side? Tell me. Someone unmute. Someone can unmute and tell me.
Phi prime,
comma.
phi.
Yeah. Close the bracket and then put a star. Huh?
Yeah.
Okay. In bracket notation, what is that? Okay. Is fine? Is this fine? In
Yes.
bracket notation, please tell me.
Yes, sir.
Just put up like this. This one is a K, a bra. This one is a K. This one is a bra. This one is a K. And also don't forget to put the star because this is the relation how it is. Now what is psi prime? What is psi prime? What is this? Psi prime bra is given by this expression. Okay. So can I put it back here? So let me wait for a few seconds because something saving the PowerPoint. Yeah. So psi prime is nothing but your phi a dagger and then you have phi. Okay. On your right, what you should have? Tell me. I have psi prime Kate. What is that?
The operator side.
Because psi prime Kate, I have to go back to this equation, no?
Yes, sir.
So I should have A and psi, but okay, don't forget to put the star outside. Huh? So basically, if I write down this thing in bracket notation, this is what I get. Please have a look. This is not very difficult. I'm telling you, just okay. And this is true for any psi or any phi. So a relation which is valid for any phi. Okay. So if you have question from this part, please ask me. This page. If you have a question from this page, please ask me. No question? No question. Which basically means everybody have understood. No question? Devojit, are you there? Okay, is Shilpa there, the PhD student? Are you there, Shilpa?
Yes, sir.
Okay, are you following?
Yes, sir.
What about others? Vijaya is there today? Are you there, Vijaya? No. So should I wait or continue? Is this fine? Because next slide what I want to do is very important based on this.
Sir, it is okay, sir. We are following it.
Yeah. So please tell me how would I know whether you're sleeping? I don't know.
Okay.
Okay. So remember Hermitian operator. How many of you remember Hermitian operator? Tell me.
Yes, sir.
How many of you?
Yeah. Yes, sir.
Yes, sir.
Hermitian. So I'll again do this. I have done it twice. I am going to do third time, and this is the last time I'm going to do Hermitian operator. Remember, if I take I use notation Q in the last class. Let us use A. Doesn't matter. This is the Hermitian operator. Then if this what notation I used in the last class, psi or phi, that I don't remember. Let me have a look.
Q. Okay.
No, operator I use Q, but I am using A, so I'll just stick to A. I'm just curious to know which phi or psi I used.
Psi.
Psi1, Psi2.
Phi or psi? Okay.
Psi1.
I think I used, yeah. So the idea is that if A operates on phi, and then I multiply this with psi star, integrate over x. I can do it tau also. I'm just putting x. That must be equal to A operating on psi multiplied with phi star into dx. This is fine, I think. Just check. One thing I forgot. This one. Just check your class notes. It has to be this, isn't it? The first day I defined this way.
Okay, sir.
Yes, sir.
Second day I showed that this is equivalent to something else. Remember that? What is that? Because if you see, this is nothing but what? This is this quantity on your left hand side is phi, comma, not into. This one, this is nice. This is how it is written, no? Phi, comma, A operating on psi, then the whole star complex conjugate the whole thing. But again, I know that the property of this is equivalent of saying that is this fine? This is exactly what I did in the last class. I am repeating because you guys should get used to with this kind of notation. And then again, if I write it back in terms of integral, this is going to be something like rather I can, because if you are using a function, it doesn't matter. I can write like this. So this is the definition I used in the last class. Please check yourself.
Yes.
If I am doing anything wrong, please let me know. But I think this is the one I used in the last class.
Sir, we can change the position between A and psi, like that.
Yeah. You can change. You can change because I put a bracket there. Okay. Because this is I'm using basically what I'm saying that if I write this way, I mean that A operates on psi. This one. Okay. That's what I mean. And this is exactly done in the last class. See. Go and check. Okay. You can also put A and psi, which I put earlier. Okay. And now what I had here in the last page, so I have to copy this. Let me copy this. What I have now, that for any linear operator, I have got this relation, which is, can anyone tell me what should I write? I hope I want to hear from you so that What was there in the last slide? This one. I had psi
psi
dagger phi,
phi
that is equal to phi
phi prime.
a
What is
phi.
the phi prime?
No phi prime. This is how it is. This is the one. Where is phi prime? Psi a dagger phi equal to phi a psi whole star. I'm just writing this one. We derived this, no relation. Are you following?
Yes, sir.
Yeah. So there is no phi prime. There is no prime. Prime was there when I operate a dagger on psi bra, I get psi prime bra. When I operate a on kate psi, I get psi prime kate. So whenever I operate this operator on a kate, it is a dagger and a. When I operate on a bra, it has to be a dagger. So what is there? This is this relation you have the previous page. No, you have already shown. I just copied this one from here and put it here. Okay?
Yes, sir.
Now again I go back to Hermitian operator. If I write the Hermitian operator using bracket notation, what should be the expression? So let me do it. If I use bracket notation, this is called bracket. What is there on the left hand side? This has to be psi a phi. This one, this quantity psi star becomes psi bra. No, a phi. Fine. I hope you are following. Please tell me.
Yes, sir.
And what is your left? It has to be phi. Now phi star become phi bra a phi, but then don't forget to put star. Following?
Yes, sir.
Now this is true for any linear operator. No, for only A is only if Hermitian. But this relation which we had arrived at in the last page few minutes back. This is true for what?
Any operator.
Any linear operator, eh? Fine. So I am calling it, this is 1, this is 2. If I compare 1 and 2, can I have a better definition of Hermitian operator? Just comparing A and 2, 1 and 2. When 1 becomes equal to 2, tell me. Under what condition?
When a dagger equals 3 dagger.
Yes. 1 becomes equal to 2 only when so this relation, this is more general, no? So basically I have linear operators and some of the linear operators will follow this relation. So only for those linear operators for which the adjoint of that operator is equal to the operator itself, they are called Hermitian operators. Following? This is the
Yes,
definition of your Hermitian operator. I have been saying this now from maybe the first class, I don't know, from the third class. Defining Hermitian operator.
So see that. So Raushida,
Yeah.
yeah, probably this is now. I mean, you can just tell them that. I mean, this is why we commented at one time that the definition of an operator is irrespective of the function it acts upon.
Yeah, I'm going to tell that. Yeah, so it does not matter. So somebody
doesn't
asks you whether it
matter.
depends on the function. Yeah.
Yeah.
It does not matter as long as you are working with the functions which are in the Hilbert space. The integral should not vanish. Then you cannot define. Yeah. So it does not matter which function. It is independent of the function, because now what you have is the matrix representation. You can do it. We'll do it maybe today or next class of the operator. So this is fine.
Yes,
A
sir.
dagger equals to A. Are you fine with that?
Sir, I have one question.
Yes.
When we measure anything, we get real eigenvalues.
Yeah. So then I'm do that. So I have already shown you that the eigenvalues are real in the last class.
So can we say that is why our operators are Hermitian? Meaning, can we understand it
because
like
the
that?
other way.
Okay.
Yeah, the operators are Hermitian. That is why the eigenvalues are real. So that's why the operators are constructed in such a way that these are Hermitian operators, so that we get real eigenvalues. Okay. Yeah. So now, now let me do. So next 10 minutes, I'm going to do something which is very important. I would say, well, everything is important today's class and last class, because today's class and the last class, I don't think you're going to get it from anywhere. So please see the recorded video if you are not attending. I hope you're attending, most of you. Okay. So the idea is, let me do it a little fast. I have a new ket psi prime, which is this. We have done. And so let us assume that I have a basis set which is called phi I. So I can actually write this is fine. No, this is, I have done it, so I'm not going to do it again and again. And this is orthonormal, because this is just follow. This is for Hermitian operator, no? Delta ij. And also I know that, which I have introduced, that okay, that if I take this, these are the relations, which I have done. So for example, if I do this, if I do this phi I into psi, what is the answer? I'm just going to get phi I. So this is called Cj, because I'm just changing this one, but only one term will survive. So this will give you essentially what I have here, J and Cj into delta Ij, and one term will survive. This will give you here. So in other words, your coefficients are nothing but the scalar product between phi I and psi. This we have done, maybe using a function. That we have done. I think I have done it using a function. And now let us do something else. Let us do this. I take a scalar product of phi I, not with psi, but with psi prime. Psi prime is given here. So what is the answer? So I know that this is nothing but phi I, and psi prime is A, operating on psi, and it is nothing but your phi I A. And what is psi I know, but before I do that, I am making use of this. this quantity. It's called resolution of identity. It's quite very useful. If you have a complete basis set, then you have this. So I'm going to, this is 1, no, this is I or 1. So I can introduce this is here. Okay, I can put it there because this is just nothing but 1. So what I'm going to do, I'm going to put this, say I'm using a different j here, 5j, and then what is there? We have 5. This is fine. What I have done, I have just multiplied the whole thing with 1, so it does not change because the definition of 1 is shown here, which I have already showed you. And this one is equal to what? This quantity? This quantity is equal to phi I. Okay. A phi j. Okay, I put the sum here, j. Phi j. Then phi j into psi. What is phi j into psi? This quantity? Can anyone tell me? What is phi j into psi? Not into, like phi j psi scalar product. What is this?
CI.
Look at it. Phi I psi is ci. So phi j psi is pj.
PJ.
So what I have here is sum over j phi I a phi j pj. And this one, I don't want to write this thing again and again. I write it like this. What I do, I write like a I j into cj. So I define that aij is this. Essentially, phi I is an integral essentially. I hope you are following.
Yes, sir.
Not very difficult. Okay. So this is my definition of aij. So what I have here is phi I times phi. Now what is this? I started doing this, no? Now this quantity has to be nothing but ci prime, I can call it, no? So what I have here is this. So the new coefficient ci prime is your aij times. Fine. And now what I'm going to do, I'm going to now I and j, they could be anything 1, 2, 3, 4, 5, 6 like this, isn't it? We are dealing with discrete basis. So essentially what I have, I can write this using a matrix. And this is very important. Again, I'm saying because what I can do, I can write this coefficient as a column matrix like this: C1 prime, C2 prime, dot dot dot, Cn prime, dot dot dot. Because this is an infinite basis. This is equal to the matrix Aij. So what should be the matrix element? This is A11. The diagonal elements are like A22, like ANN, dot dot dot. Off diagonal elements are like this: A12, dot dot dot, A1N, dot dot dot, A21, AN1. This is 1 and okay, and then this is multiplied with this column matrix, which is C1, not C1 prime, only C1, sorry. C1, C2, Cn. Okay. This is fine. We are almost towards the end of the class. Is this fine? I'm just using matrix and writing, and this is, if this is a matrix, so I can use some matrix notation which is okay, but these are like matrix elements, isn't it? This is one of the matrix elements, Aij. So if it is A11, now again I'll spend 5 more minutes maybe on Hermitian operator, which is very important in quantum mechanics. What I had here, I remember what you had here. So this is phi I a phi j, isn't it? So remember the definition of Hermitian operator. Hermitian operator's definition. What is the definition of Hermitian operator? Which I have done in the law. Okay. But before I do the Hermitian operator for any linear operator. Any linear operator I take, and I now use this basis function in order to basis function. If I use basis function, phi I a dagger phi j, this has to be equal to what? Tell me. Remember, no? Phi j a phi I, but don't forget to take the star of the whole thing, isn't it? We did that just few minutes back. If you don't remember, you go come here and see. This is exactly this. I am just now calling phi I and phi j. Okay? Is this fine? Now I have shown you that, okay, this is a matrix element, isn't it? So basically I can call this as A I J dagger. Can I call it Aij dagger? Just follow the definition. Aij is this, then this has to be Aij dagger.
Yes, sir.
And what should be the on the right hand side? A Ji, but then don't forget to put what?
Complex star.
Start.
And now this will bring to something which you already know. What is that? You know Hermitian, you know adjoint matrices, isn't it? I think all of you or many of you know adjoint matrices. Please tell me if you know about adjoint matrices.
Yes, sir.
Yeah. So this is essentially the same thing what I have done here. Look carefully, very carefully. What I have done here is I am saying that taking adjoint is equivalent of what? Changing rows into columns. And taking
Column
complex
into
conjugate, isn't it? Okay, this is exactly, no? Your Ij becomes Ji means you're changing rows into column and then putting complex conjugate. Because if I take a two small matrix like this, if I have A11, A12, A21, A22, okay, dagger of that is going to be what? It is going to be A11, A21, the first part, sorry, not 21, A12, sorry. A12, A21, A22, but that is not enough. What should I do? I should take complex conjugate.
complex conjugate.
That I know, that you know, all of you? Huh? Okay. So So this is what do I mean by, I did not tell you at the beginning, if you use the matrix, what do I mean by taking adjoint? So the operators can be represented using matrix, and you can take conjugate. And the last thing, which you should not take more than 2 minutes, again Hermitian operator. This is for any linear operator. For Hermitian operator, what is the answer? For Hermitian operator, I know that A dagger equals to A. Remember? This is the definition. So for Hermitian operator, this relation Ij has to be equal to Aj star. So for Hermitian operator, there is, since A dagger equals to A, I have to do on, I have this condition that Aij equals to Aj star. Okay? What does it mean? It means two things. When I equal to j, what happens? Tell me.
Square matrix.
No, don't say. I equal to j means these are the diagonal elements, isn't it? These are diagonal elements. I am dealing with square matrix only. So these are diagonal elements. A equal to j, it basically means two things. First of all, number one, it tells you that any two elements which are symmetric around, not around or with respect to the principal diagonal. Gonal are what? Complex conjugates. Can you see that? Basically, I have a, if I take a square matrix, say 3 cross 3, you have the diagonal elements. We'll talk about it later, but all the out diagonal elements, okay, symmetric with respect to the principal diagonal, they are complex conjugates of each other. Okay, of each other. And the last one is very important. Can you see the diagonal elements are real? Because diagonal elements means what? I equal to
Eigenvalue.
I equal to j, yes. So because if I do this, what I'm going to get? I'm going to get aii equal to aii star. This is possible when? Only for a real number, the complex conjugate of that number is equal to that number, isn't it? And that has to be because the diagonal element that gives you the eigenvalues. Because if I have phi I, a phi I, and if a has the eigenvalues epsilon I for phi I, that will come out, it will give you epsilon I, and phi I are orthogonal. Okay. And that is important. And the first point, if you don't understand, think about it, not very difficult. we can do in the next class, but kind of die because I'm saying that AII equals to phi I A phi I, and this is equal to epsilon I into phi I, and this is equal to epsilon I. And this is an eigenvalue, so it has to be real. So now, after so many classes, I have kind of proved that the eigenvalues of a Hermitian operator are real. Eigenvalues are real. But this is not the definition of the Hermitian operator. It is only one of the consequences of Hermitian property of an operator, linear operator. And the first point, it says that any two elements which are symmetric with respect to the principal diagonal are complex conjugates of each other, and that is obvious because if I take, say, A12, it says that here you see that it says that if I take A12, it tells you that A12 has to be equal to A21 of star. So A12 is which one? This is the principal diagonal, this one. So A12 and A21, what is the relation between them? One has to be the complex conjugate of the other. Can you see? See this one? Yeah. So basically A11 and A22, this is the principal diagonal, and these two are the elements symmetric with respect to the principal diagonal. So these two elements for a Hermitian operator has to be complex conjugate of each other, isn't it? Are you following this? Are you following?
Yes, sir.
So basically, if I give you a matrix, like just matrix, I'm giving you one matrix. Say I give you a matrix, say like 0, 4, minus 4. Okay, let me not do it today. We'll do it in the next class because I don't have time today. But these are the properties of Hermitian operator that I have done today. So I think we will conclude, but in the next class, I think we will go back and start the hydrogen atom, go back to some chemistry problem and do this. But few things I should say, that okay, I should say that okay, your AB, if I take AB dagger multiply, this is equal to B dagger, A dagger. Or if I take A plus B dagger, this is equal to A dagger plus B dagger. All these things you should try to prove yourself, okay? Okay, you should try to prove yourself. I think there are a few more properties which you can go and try to prove yourself. Not a bad idea to do it. Also, if you take A dagger of dagger, then it's called A lambda A of dagger is actually lambda star.
Hello, sir.
A dagger. And also, if I have a situation, let me finish. A dagger equals to minus A. Okay, then A is called anti-Hermitian operator or matrix. So with that, we'll conclude, and I'll stop recording. And then I can have few minutes and I can try to answer your questions, whatever you want to do. I think I'll do that. And now stop recording. Thank you very much.